Hello. So here we will talk about more about orders of elements in a specific type of a group, in a cyclic group. And the specific model, which will be convenient for the story, will be of roots of unity, complex numbers, which solve this equation. And using Euler's notation, using trigonometric form, we can label them effectively, and starting with, say, this root, we can list them all as powers of that root. And the powers will be, because of the cycling behavior of that complex number being of order n, the powers will be really integers mod n. So that is in effect an identification between this cyclic group and that cyclic group. But yeah, that is an effective way of counting roots and seeing that they're exactly n of them. So let's look at the distribution of orders of those roots, of complex roots of 1. Namely, let's count how many complex numbers have a given order. So first of all, what is possible order? The order, by the definition, is the smallest power which is equal to the identity element. And that has to be obviously a divisor of the degree of the root of n. So yeah, let's look at the situation when we have a root which is of order d. Well, we can just forget about degree n and say that this is degree d root. And yeah, that's because these roots are among the roots of degree n. And in here it will be primitive. So primitive is just to have this maximal order. The order has to be the same as the degree. So let's just count the number of primitive roots inside here or inside here. So there's number of primitive roots. Of degree n. And okay, so just by the definition, any root at all is a power, and we want it to be such that the smallest power of that power, which is equal to 1, is n. So that means that that power should not divide into n, right? So L is equal to n. Of course it works, but it works only so that is the smallest power if k is not a divisor. If it is a divisor, we have complementing number which will give us n in the product, and that will be smaller than n, that complementing number. So the condition for the power or the corresponding complex number, I know this notation, to be primitive as a root of 1 is that this label k is coprime to 1, sorry, coprime to n. The number of such considered mod n is counted by the Euler's function. So here we have our first counting result, that the number of primitive roots of degree n is the Euler's function of n. And here is the second counting result. Let's just see how many times each degree appears. So total number of roots of degree n is n, and then we can expect for any divisor roots of degree d inside roots of degree n, and those roots we can look only at primitive such, and the number of them will be the Euler's function. And here we have the formula that the sum for all the divisors of n of Euler's numbers is equal to n. So again, these are just the counts of elements of order D. And since any cyclic group is as good as any other, so this for example, this is a result of about orders of elements in an arbitrary cyclic group. So now we can apply it to not just roots of 1, but integers mod n, or integers mod a prime, but under multiplication, so non-zero integers modulo a prime. So all these groups are cyclic, and then the number of elements of a given order in any of them will be given by the Euler's function, and then the total number of elements will be separated among the orders in this very way. So maybe just a bit more of a general group theory reformulations of what we have observed here. So let's imagine again a generic cyclic group of order n. So this statement is as follows, generalizing to the arbitrary cyclic. Let's look at a subset in the cyclic group of those elements which solve this equation. So that will be this analog of degree D roots inside degree n roots. So that is a subgroup in G, and that is a cyclic subgroup, and the number of elements, if D is a divisor, the number of elements is just D. So that's what we saw here. And more generally, if G is not necessarily a divisor, then we can replace this number by the divisor of n, namely the greatest common divisor of D in n. So these two solution sets are the same. What it is saying is that if we're solving this equation and we are inside a cyclic group where we have to obey this equation, it's the same as to solve this equation. So that's what this set equality means. And maybe just finishing with sort of recycling this argument again in a more general setup. So making a more general statement, we'll call it lemma, about computing the order of the power of some element. So that's what really happened here. And computing in terms of the order of the element. So okay, let's investigate. Let's fix this order of element G to be n. So that means that the first power of G, which is identity, is the nth power. And then we want to compute the order of a power, some other power of G. Well, again, we want to find the first such that this is the identity, but that can be only the identity when it is some power of G to the n. So we have numerical condition that K product with L is a multiple of n. So what is the smallest solution for L for this equation? Well, obviously it has to be the greatest common divisor of K and then divided into n. So that is definitely works, and that you could argue, say, if you like, using the fundamental theorem of arithmetic, it's the first time it works. So here we are. The sort of sleek answer is that we have to take the order, this n, and divide the greatest common divisor of K in the order divided by. So that is another useful formula for computing the orders of powers, effectively in a cyclic group generated by G. That's it. See you later.